This talk discusses aspects of the HDF5 data model that present challenges in UI design. Where do they exist, and how can we render the model using designs that are effective across all ranges of HDF5 data stores? So the UI rendered here is captured via screencast of H5S, which is a native Windows C++ desktop app. It's written to the C API of HDF5. So some areas where large data models impact UI. Clearly groups with large subgraphs. There's a similar but separable problem, large number of attributes. We have to deal with deeply nested group hierarchies. And then there's data spaces and their associated data storage that can have high rank, even data types with high rank. And certainly we can't forget descriptive naming conventions that are important in HDF5. So we'll walk through some of the individual design areas here in the UI, and we'll deal with them independently, but ultimately they're all interdependent. First thing, we want to take a look at modifications to the node expander, and then we want to give special treatment to attributes. We'll talk about scrolling at the group level in the graph, and then techniques to help with geometry management at the left and the right. When working at high graph depths, we have vastly underutilized areas on the left, and then long names give us problems on the right. So before looking at the individual UI elements, though, a few words on two design principles to frame the design going as we consider it. We'll start with the second rule first, and that is we would like the capability of expressing an HDF5 name data object in a single line using only pure first order HDF5 data terms. Understanding one of the data objects shouldn't require any further mouse clicks, hovers, or pop-ups. And then it's a recognition that even given the complexity and all the power of the HDF5 APIs, the data model is very clean, and we want to try to express it very clearly. So before looking at the schematic, we'll just read the one-line example here. Go left to right. It's a data set named kappa lambda, three-dimensional data space. It contains two-dimensional arrays of integers, uses chunk storage with 3 filters. Someone has nicely provided a comment. There's 9 gig of ints. The data space is approximately 1K by 512 by 64. It's arranged in 512 by 128 by 8 chunks. Each element is a 16 by 16 array of ints. And that's it. That's kappa lambda in one line. Now, when we look at the schematic, I've highlighted the layout of the data space and the data type and the storage. And it's not readily apparent here, but one of the requirements is that the expression has to visually degenerate nicely. That is, as the HDF5 object gets simpler, which it certainly can, the one-line expression has to simplify cleanly and without complication. And the other thing is, while the HDF5 first order vocabulary is very logical and understandable, it's a rich vocabulary nonetheless. So getting everything into graphical notation certainly takes some work. And we won't go into each glyph here, but we have the data space notation, and I give a quick look at the data type notation. And you can see with compound types, that's where the first order vocabulary stops. We don't descend recursively into the compound type. Finally, if you look at the very lower portion, you can see that we actually can give strings very thorough treatment, even overloading the string length on a suffix of the data set name. And then just to go back, rule number 1 is we want to design for visual worst case scenarios. So now we're going to look at how we do that. And the first element to consider is a modification to the node expanders themselves. So to the conventional 2 states of expanded or collapse, we add a third tri-state position, which is denoted in the body of the expander with a small forward slash. So what's the purpose of the tri-state expander? In conventional hierarchical displays, when the graph is scrolled top to bottom, nodes just scroll off the top, and the lineage of the topmost node in the view gets lost. So here, the parent node expanders in the path of the topmost data object are preserved in cascaded fashion at the top of the view, but they're put in a tri-state position to indicate that at the current scroll position, there are out-of-view children between this node and the next child node in the path. And one feature of the tri-state expanders is then that they are completely functional, making each parent of the topmost node always accessible to the user. First click fully expands the expander, the next click fully contracts it, the next click expands it, and subsequent scrolling throws it into the tri-state position. So we want to use these when we render the attributes. We render the attributes with special consideration given their role as important parts of self-describing HDF. So we do this in two ways. To start, we append the attribute expander to the label of the object to which the attributes are attached. So now attributes are expanded and collapsed independently of expanding the data node in the graph. Also, attributes aren't edges in the graph, and it's good to reflect that as well. So you can see that they're rendered slightly differently with respect to the indentation and sightline beads. And this is going to help give additional distinction to attributes that proves useful later. Now, the second part of this is we use the postfix expander combined with its tri-state function, and we're going to scroll attributes differently from the rest of the graph. When scrolling downward to the bottom of the graph, the attributed object stays in view with the tri-stated expander until the last attribute is scrolled. So the object of attribution is only scrolled out of view when all the attributes are rolled up. Then in reverse, when scrolling to the top of the graph, the data object comes into view first with its attribute expander tri-stated and remains in place until all the attributes are unrolled underneath it. The design goal is to never have the object of attribution out of view when any of its attributes are in view. And again, this will factor in later in our techniques for scrolling. And now we can turn our attention to the design challenge of adapting traditional hierarchical graph display to better handle the display of very large HDF5 groups. Specifically, we want a good solution to the problem of displaying items in a hierarchical graph where subtrees are themselves very large graphs. So part one of this is make the group scrollable. And to do this, we're going to need 3 cooperating microcontrollers. We'll start with the microcontroller in the center. That's the sightline bead of the group that descends from the group node expander. Notice the T's on the bead give an easy indication of the immediate children of the group. On the right is the introduction of a flyweight scroller, and on the left is what appears to be a traditional scroll bar, but it actually has a more complex functional responsibility in the scrolling mechanics. So the flyweight scroller is a translucent glyph. It can be placed anywhere on the viewing surface. And here we're going to use it in a very specific way, but it's a fundamental part of solving this general problem that arises when multiple scrollable objects exist on a display surface, which is precisely what we have here. We'll drop it on the successive group sightline beads. And with a specific group sightline triggered, we can see the scope of the group. The upper and lower bound of the outer shaded region shows the first and last child of the group. The lighter notched region shows only the visible children of the group. Moving upward in the graph or left along the sightline beads, it eventually brings us to the root group, and you can see the begin and end markers are at the limits of the global scrollable bounds. And then when the flyweight scroller can't find a scrollable object, it scrolls the global graph scope. And when we activate the sightline bead of the platform group, what happens is we link all the microcontrollers together, and then for the purpose of this illustration, we'll just wheel scroll to the bottom of the group, and then we can wheel scroll back to the top. And you can see that the group won't be scrolled anywhere past its upper or lower limits. So you can just speed scroll the group as you see fit. But that's just the first part. So we have to now, we have the prerequisite for handling large groups, but we need the second piece, and we'll continue with the platform group that was shown earlier. So with the flyweight scroller attached to the platform sightline, we can see the scope of the group. Note the visible portion of the group, which is shown in the inner notched area, is at the upper limit of the full scope of the group. A scope frame now is a way of constraining this visible portion. So we'll walk through the mechanics of imposing a scope frame on the platform group. So we're going to take the following actions. On the node expander for platform, we use a mouse down with setup and hold. Once the setup time is achieved, a small cross appears just off the upper right corner of the expander. On mouse up, a scope frame is now placed on the node, and the number of children displayed is limited to the frame size, which in this case has a preset of 16 elements. To remove the frame, simply repeat the setup and hold. Once the scope frame is applied, the node can be expanded and collapsed as usual. It retains its upper right marker to indicate a scope frame is always present. And scope frames can be applied or removed in either the collapsed or the expanded node state. We'll take a look now, the schematic of the scope frame as is rendered on the descending bead. It shows the following. There are two crimps that get inserted on the bead to indicate the begin and the end of the frame. This is where we're potentially introducing discontinuities into the hierarchical display. In this case, a single crimp is shown at the top of the frame as there's no initial discontinuities. A double crimp at the bottom to show that a discontinuity now exists between the last elementum in the frame and the next element displayed in the graph. And also note that the scope frame does not include the attributes of the node where the frame is inserted. The frame starts at the first child of the platform, not at its first attribute. Next, we'll attach the Flyweight Scroller to the node and scroll again using the mouse wheel on the triggered scroller to get single step scroll to help us with this illustration. When we scroll downward through the frame, note the jump discontinuities being created due to elision of the portions of the subtree outside the frame. Because we're interior to the graph though, letting these nodes scroll off the top of the frame is just not acceptable. If we did it, the user loses vital contextual information about the frame section of the graph. And with the loss of context, the hierarchy doesn't make sense the way a tree is supposed to make sense. There's just too much loss of visual coherence, given that we've disrupted the collapse expand view of the graph. But with the tri-stated expanders cascaded across the top of the frame, we get the visual order back. The user has all the visual cues required to convey the elided children between the expanders, and this imparts the necessary visual bearings when viewing the framed part of the graph. Now, handling the discontinuity at the bottom of the frame is important too, but the discontinuity is not as jarring, and it's achieved by placing a small X glyph on the beads to emphasize the discontinuity. Then when we scroll to the bottom of the frame, the lower scope frame crimp switches from a double to a single, and the truncation X patterns on the sub beads are replaced with termination T's to cap them off. So we'll illustrate three things real quickly here. Keeping an attributed node visible at the top of the scope frame with its tri-stated attribute expander contributes to never losing the sense of a visual path to the elements in the scope frame in spite of all the discontinuities that are present. And we can demonstrate here, tri-stated expanders are completely functional within the scope frame. And we can also scroll individual nodes across all depths within the scope frame as well. The caveat we have to mention here is that once scope frames are introduced into the graph, we have the requirement that all other scrolling aware microcontrollers have to be scope frame aware. And this is where everything else comes into play. So in the example shown here, scrolling at the root group must handle the discontinuities induced by scope frame when scrolling at this global scope, with a 16 element scope frame applied to the data 40 Hertz node, and with the node scrolled approximately to the midpoint. The scroll bar on the left has to show the jump discontinuities as we scroll into the scope frame, and also as we scroll out of the frame, which we'll show here. So then the scroll bar has to be updated to indicate that we've crossed the scope frame boundary, and now we're in essentially a completely different section of the graph. And then as we scroll back up, And the other thing we have to mention too, that visual corner cases do arise, and we want to know how to visually handle underflowing the scope frame, or how to use upper and lower justification for scope frames that are in partial view. And getting the mechanics and the visuals functionally correct takes some care, but overall scope frames turn out to be pretty well behaved. The next thing we're going to look at here, this is a bit of a perfect storm. We have high graph depths, we have very large subgraphs, and we have descriptive names. We'd like to deal with the problem here without horizontally scrolling HDF5 objects off to the left and losing them. Additionally, we don't want to change the indentation, because shallow indentation produces some very unfavorable visual results. So we'll use a graph depth indicator at the bottom of the graph to show the working depth, and then we will opt for justification over scrolling. And you can see each HDF5 object, as it reaches its depth level in the graph, it's fixed at the leftmost sight line. It's annotated then so that the user always has a visual reference to the graph depth for every object in view. And then when the graph gets completely left justified, all the attributes are collected nicely at the left margin, and they're aligned for easy viewing. Finally, we'll just scroll up to the top with a completely left justified graph. And when we get there, we'll reset the graph depth to 0.
Rob,
I have one more minute.
Okay.
Yes, thank you. And descriptive naming is the last part, and it's a critical part of HDF5. We can make 2 observations. Usually there's a high degree of sameness among siblings, and where the differences occur, often they're at the beginning or the end of the string. So rather than truncate, we'll opt to elide from the middle of the string. And then if the generalization holds, it has the effect of giving the user a visual hash to the full name. And it also has the benefits. It works very fluidly with scrolling, and it flows nicely into and out of justification. And that concludes the presentation. I will stop my share, and I'm done. That's it.
Thank you. And any questions for Robert?
Would you like me to read the questions from the chat?
Yes.
Yes. Is this Windows only? Yes, that is correct. It is Windows only, and it's not based on Qt, but it is based on technology that actually initially came from Linux world. But it has not been ported. Those layers have not been ported, but they originally came from there, and they were moved to the Windows the Windows platform to make this app. And I did not show the display of hard links and soft links in the one-liner description. I also forgot to mention, this is NASA's ice sheet altimetry data. I wanted to give credit there, but I didn't. I neglected to put that on the slide. That didn't show any hard or soft links, and I did not include that. I think if you looked on, yes, I think if you looked on the vocabulary for the data space, you'll see how the links are represented there. So I'd have to go back and look, but that should be included in the glyph notation for the one-line expression for an HDF5 object. Does it read the entire file structure at once? It reads the entire file structure at once and constructs the graph. It doesn't do anything with the data, but it does read everything it needs to construct the graph topology. Yes, Mark.
Yeah, this is my folk. Robert, this is brilliant and elegant. I've been admiring it for years, your work for years. I keep stumbling across it, and I just think, man, somebody has finally really thought through so many different things. So I want to thank you for doing this.
Oh,
but I've had this frustration because until now, I didn't know who was behind it. And I didn't, based on what I could find on the web, I couldn't find an email or somebody to write to. Is this a tool? Is this something that we can get our hands on? Tell us a little bit more about, what you're
Yes.
up to, what this is all about, what your goals
Yes.
are with this, and so forth. Thank you.
Well, the goal ultimately is, and I'm always encouraged because there's so much development in terms of the expanding HDF5 data space that having the ability to look at models wherever they exist is becoming this tremendous opportunity. And so writing the scanner like this to expose these models and let people know what's out there is very exciting to me. So it is available as a native Windows application, and getting it onto more platforms is beyond what I could do with
Sure.
the resources that I have. But yes, this is the overriding goal really is to make it so easy to see what's in an HDF5 data store, regardless of where it is. And this is the good starting point. And so that's what, so this is I released the native application without charge at the moment to get feedback and to get real use cases on it, and also friendly users, because as an independent developer, it's difficult to really test all the corners that you need to test for a UI application like this. But the application is available, and we can certainly speak, and I can get that set up.
Okay, thank you. Thank you
very much. Thank you, and thank you very much. Thank you very much for the compliments. I appreciate it.
It's a thing of beauty. Thank you.
Thank you.
All right, any other questions? So we are in a break now, coffee break now.
Okay.
Okay, if no questions, thanks, Robert, again.
Yes, thank you. Such a smooth
Thanks,
presentation.
Elena.
Yeah.
Thank you. Oh, I would also say thanks. I put Lori through a couple practice sessions on Zoom. I think I was pushing my limit there, but she was very nice in making sure that the video was playing, because I did have concerns about the resolution.
No, it was great. Yes, and it's such an elegant presentation. And we're struggling. We have the old tool HDF5, and this is this is something long overdue. Hopefully, we'll be able to create some portable, but there are many lessons to learn, especially in design, how to look at HDF5 data, and really one click, easy to navigate, and
Yes.
kind of deal with a huge amount of data we have. And hopefully your tool, when we have, all drivers and rules available, it will be, talk to different storage, which is good.
Yes, and I also like to think of things in terms of the engineering problem and the design problems, and because they're the engineering problems, we can solve them. The design problems, those are where it gets really tough.
Yes.
Have you thought about adding swimmer capability? Because swimmer works on Windows if there is GPFS system filed or it's local.
Yes, this is one of the areas that I need to focus some attention on, because I really would like to make have the lower layer needs to be wherever the HDF group is at in terms of its functional capabilities. This application should support that as well. And so there's work to do in making sure I can get everything packaged up and delivered with the application, because I try to stay in lockstep with the latest HDF stable release.
But it's also a design problem how you present, and with VDS it's the same, right? How you present that functionality in design.
Yes. So there's a lot of many things to consider there. Yes.
Right. VDS probably a little bit, yeah, it's still challenging when you think about it. What is the best way?
Yes, well, and also I've spoken a little bit with Lucas on because the possibilities with the user-defined functions in HDF, that would impact an application that's such as this, because and there's some tremendous possibilities there as well.
Right, right, right. Yeah, thank you.
You're quite welcome. I appreciate it. Thank you.
Thank you.